Hello students, welcome back to school. My name is Mr. Urby, and this is going to be my class teaching physics. I'm really excited to be back with you guys teaching. I know it's been a wild year, but we got to get back to our learning routine so that we can keep growing and we can achieve our goals. In this video, I'm going to cover some basics with graphing, in particular position versus time graphs and how those are useful. We're going to start learning about one-dimensional kinematics, which is the study of motion in one dimension. One dimension just means that we're going to be looking at examples of motion where things move forward and backward, or up and down, or left and right, or all kinds of situations where things are just moving in a line back and forth. There's another video for today accompanying this video, and that one's going to be more focused on the syllabus, the rules, and expectations. But this is the video where you're going to find the instructional content for today's lesson. Okay, for today's lesson, the three topics I'm going to cover are position versus time graphs, distance, and displacement. Okay, to start off, we're going to go with position versus time graphs. When you hear the word position, some things that come to mind should be where something is located. Okay, so of course, whenever we're studying motion, we are concerned with where something is and how its position changes in time. Now, graphs are a super useful tool in visualizing something's motion. With a quick glance of a position versus time graph, you can more easily understand the motion of an object as opposed to looking at a table of a bunch of numbers where you'd have to think a little bit more about how that object is moving through time. Okay, I'm going to draw a simple example of a position versus time graph. Here I have my x-axis on the bottom and my y-axis on top. On the x-axis, I'm always going to have time. Okay, so in this case, time is the independent variable, and we measure time in seconds, so I put a little s here in parentheses. On the y-axis, I'm going to go ahead and put position. All right, and whatever goes on the y-axis is the dependent variable, because this variable depends on this variable. So the position is dependent on the time in this case. All right, if we were to map out the motion of a squirrel running down a power line using a position versus time graph, I can describe a scenario of that squirrel's motion and try to map out its journey with a graph. So let's try doing that. Let's say the squirrel starts off at a light post, and we'll declare that that light post is position 0 meters. Let's say the squirrel moves for 5 seconds in a straight line down that power line, and let's say it moves at a constant speed during those 5 seconds. As the squirrel moves down that power line, its position is going to get further and further away from that initial light post. So my graph is going to look something like this. So here the position of the squirrel is moving away from the light post, and this is going to be going in the positive direction. So generally speaking, on graphs, when the lines move upward, that's the positive direction, and when the lines move downward, that's the negative direction. Anyway, let's say after the 5 seconds of moving down the power line, the squirrel got 10 meters away from the light post. I would make a tick mark right here and write 10. So I know that at 5 seconds, the squirrel was 10 meters away from where it started. And let's say the squirrel just sat there on that spot for another 5 seconds. Okay, well if the squirrel sat there at the same spot, then I know that its position is not going to change. So it's just going to be a flat line for the next 5 seconds. Alright, and after those 5 seconds, let's say something further up the power line scared the squirrel back to run the other direction where it came from, and it ran for another 5 seconds, but in the opposite direction, the negative direction, back to where it came from. This is what my graph would look like for that entire situation. So just glancing at this, I can see that the motion involved something moving away from the reference point or in the positive direction, and then it stopped for 5 seconds, and then it moved back towards the reference point in the negative direction. So from 0 to 5 seconds, it moved in the positive direction. From 5 to 10 seconds, I can see that it didn't move at all. And then from 10 to 15 seconds, I can see that it was moving in the negative direction. In today's activity, you're going to do something similar with a position versus time graph, and you're going to have to analyze when a particular character is moving in the positive direction, negative direction, and when they are staying still. So you can refer back to this video to make sense of that part of the activity. The next two concepts I want to cover are distance and displacement, and how those two things are different. All right, distance is the total distance traveled. That one may be a little bit more self-explanatory, but it's important to distinguish the difference between distance and displacement. So let me just apply this concept to this little example we did here with the squirrel. So distance is the total distance traveled. What would be the distance traveled of this squirrel in this example? Okay, well I can see that from 0 to 5 seconds, the squirrel moved a distance of 10 meters. From 5 to 10 seconds, the squirrel didn't move any distance, so 0 meters. From 10 to 15 seconds, the squirrel moved from the 10 meter position to the 0 meter position, so that's another 10 meters. Alright, so in total, I'm going to add up all the distances that were traveled by the squirrel over the entire course of the journey. It was 10 plus 0 plus 10. So that's a total of 20 meters. Alright, so the total distance of the squirrel was 20 meters. The other term I brought up was called displacement. Alright, the displacement is how far the object is from the starting position. If I wanted to know the total displacement of the squirrel over this journey, well, I know that it started at position 0 meters and it ended at position 0 meters. So since it ended up where it started, it didn't really go anywhere, so its displacement would be 0 meters. If I wanted to know the displacement from 0 to 5 seconds, then I would see that it started at 0 meters and ended up at 10 meters. So the displacement in that case would be 10 meters, but for the entire duration of its journey, since it ended up where it started, the displacement is 0 meters. So as you can see, distance doesn't care about what direction the object is moving, whereas displacement does care about the direction. We call terms that do not care about direction scalars. Okay, so scalar variables do not care about direction. We call variables like displacement that do care about direction vectors. Right, so because displacement does care about the direction, it is a vector. We're going to learn more about the differences between scalars and vectors as we continue through this class. And for the rest of this week, we're going to be focusing on position versus time graphs and applying the concepts of distance and displacement to those graphs. Alright, I hope this video helps you guys understand these concepts, and I hope it helps you finish the assignment for today. If you have any questions, please let me know. I'm looking forward to working with you all, and thank you and have a nice day.